Hey folks, welcome back for another lesson in vectors. In the last lesson, we looked at converting between different representations of vectors in the two-dimensional world. Our goal today is to take that and move it forward a step by looking at 3 dimensions. So we'll start by looking at the magnitude of a vector in 3 dimensions. After that, we'll look at direction cosines, which is a way of representing angles in 3 dimensions. And then we'll look at a related issue, which is off-axis unit vectors. By the time we're done, you should be very comfortable with the various representations and converting between those representations in both 2 dimensions and 3 dimensions. So let's get started. So our first topic here today is magnitude in 3 dimensions. We've previously seen magnitude in 2 dimensions, and it was a very simple application of Pythagoras' theorem. And we saw that if we have a vector presented to us in components or in unit vectors, we simply take those components, square them, sum them, take the square root as per Pythagoras, and we have a solution. So we see that example of minus 10 in the x direction, plus 6 in the y direction. We saw the same example last time. That gives us a total displacement of 11.7 meters. And the solution is straightforward. We punch numbers into our calculator, square some things, take some square roots, and we're done. What happens when we move into 3 dimensions? In 3 dimensions, it turns out that we simply do the same thing. So we square all 3 of our components, we sum them, and we take the total square root. Now, if you've never seen this before, it may not be really obvious that that's correct. So let's have a look at where it comes from. So let's start by drawing out our 3-dimensional vector. It's a little difficult to do that in 2 dimensions, but here it is. We've got a 3-dimensional vector. We'll call it v. We have v in the x direction, v in the y direction, v in the z direction. So we have 3 components for a full vector of v. Now what we're going to do is we're going to name that diagonal dashed line S. We know that the magnitude of v, based on what we've already learned and based on straightforward trigonometry, can be found by applying Pythagoras to vy, s, and v. So the square of the magnitude of v is equal to the square of the magnitude of s plus the square of the magnitude of vy. But here's the thing. We can also see from the diagram that s, vx, and vz form a right triangle. So that means we can apply Pythagoras again, and we get the square of s is equal to vz squared plus vx squared. We take that and we substitute it back into our original equation, and we get the sum of all 3 components, vx, vy, vz. So our magnitude of v is simply the square root of the sum of the squares of our components, which matches with the result we reviewed just a minute ago. So again, the result is, if we have a vector presented in component form or unit vector form in 3 dimensions, we'd like the magnitude of that vector. We simply square all 3 components, add them together, take the square root, and we're simply applying Pythagoras in 3 dimensions to get our magnitude. A little note on notation here. We haven't seen this before, but we'll see it again. We've already seen that we use a non-bold D, for example, if we're dealing with displacement, to indicate the magnitude. Another thing that we'll see routinely is the bolded vector D with absolute value bars around it. Those bars have different names depending on what book you look in. Sometimes they're referred to as an absolute value sign. Sometimes they're referred to as a modulus. Sometimes they're referred to as a magnitude. And really, magnitude is what we're using it for here. So the magnitude of the vector D is equal to non-bolded D, which is equal to the square root of the sum of the squares of the components. Okay, so what we're going to look at next is off-axis unit vectors. So we've already seen the special cases of I, j, and k, which are the unit vectors indicating the x, y, and z direction. Sometimes it turns out we'd like unit vectors pointing in other directions. So we might, for example, have a vector, let's call it v. We might like to know what the unit vector pointing in the same direction as v happens to be. Well, we know that in the scalar world, if we take some value and we divide it by itself, we get a magnitude of 1. Wouldn't it be nice if we could do that with vectors? Unfortunately, the vector v divided by the vector v is undefined. It's not obvious right now why that is. We will see why later on when we talk about dot products and cross products. So unfortunately, we can't just simply divide the vector by itself to get a vector of 1. However, if we were to take a vector v and divide it by its magnitude, that is defined. What we're going to get there is the unit vector e in the v direction. So what is that? E in the v direction is going to be the v vector, which we can spell out here in components or in unit vectors, divided by its magnitude, which we've already seen how to get. It's simply the square root of the sum of the squares. And we can actually split that into separate components. So the unit vector v is going to be equal to vx divided by v times I plus vy divided by v times j plus vz divided by v times k. When we divide each component by the total magnitude, what we'll end up with is a unit vector that points in the same direction as the original vector. So the final topic of the day here is direction cosines. Direction cosines follow fairly closely from unit vectors in the direction of a general vector. Let's say again that we have that vector v, we've determined what the unit vector ev is in the same direction, and consider three different angles, alpha, beta, and gamma. Alpha is the angle between the x-axis and vector v. Beta is the angle between the y-axis and the vector v, and gamma is the angle between the z-axis and the vector v. We can see here that the cosine of alpha, the angle between v and x, is vx, the component of v in the x direction, divided by the magnitude of v. And we just picked that out from straight up trigonometry. Similarly, if we look at beta and gamma in the y and z directions, the cosine of beta is vy divided by the magnitude v. Cosine gamma is vz divided by the magnitude v. These are called direction cosines, and unfortunately we won't have a lot of opportunity to use them in this course. However, again, if you do more advanced studies of vectors or of mechanics, they show up quite a bit. It's worth noting that if we look back at our unit vector, EV, Vx over V, Vy over V, and Vz over V are the direction cosines. So we can represent our unit vector EV as cos alpha I plus cos beta j plus cos gamma k. So we don't have to represent it as components divided by magnitudes. We can also represent our unit vector in terms of the direction cosines. It's worth noting that the magnitude of EV is 1. By definition, it's a unit vector. That's the whole reason unit vectors exist, is because they have a magnitude of 1. And so if we try to take the magnitude of EV using the three-dimensional Pythagoras, we discover that the cos squared of alpha plus the cos squared of beta plus the cos squared of gamma equals 1. And there you have it. Now you know how to work fully with vectors in 3 dimensions. You can find the magnitude of a vector in 3 dimensions. You can look at the angles of the vector represented as direction cosines. And you can find unit vectors along vectors that are not coordinate directions. In the next lesson, we're going to move on with our manipulation of vectors by looking at the first form of vector multiplication, which is called the dot product. That's also known as the scalar product. I'll see you then.